Okay, all right, so let's get started. So today we'll continue with classification, and basically the idea is to give you some idea of how neural networks work, right? So we're gonna cover neural networks today. We won't, get even close to looking at sort of everything in neural networks. It's a very popular and sort of very broad topic. But I'll give you some sort of intuition on why they work, then how they are trained. Basically, again, as you get your, some algorithm that we're trying. Okay, at least the idea of what neural networks are trying to do. Okay, so basically, neural networks, in some sense, came out the need to sort of automate this kind of things. When you're let's say from last time, we're saying if you have k classes, how do you, classify? Right, how do you classify from 1 to k instead of 0 to 0 and 1? And then we saw two things, right? One is something called one against all. Basically, you train k classifiers. Each one of them saying is it m or not m? Let's say you have m possibilities, and then you have SVM. You just compare to say that is it class 1 or not class 1? Is it class 2 or not class 2? You train k of these. And then basically at the end, you can just, for each x, look at all your SVM, right? Look at all these kind of functions and just pick the largest one, right? So this is how you do if you have more than 2 classes. Instead of asking, is it, 0, 1, 2, 3, 4, you ask, is it 0 or not 0? Is it 1 or not 1? Is it 2 or not 2? And at the end of the day, you pick the most confident one, whichever where this thing is the largest. So this is one against all. You can, of course, do one against one. Right, so you have SVM. Instead of doing as a class 1 or not class 1, you can look at all pairs of I and J. You can ask, is it class 1 or class 2? Is it class 1 or class 3? Is it class 1 or class 4? Look at all those kind of comparisons. And at the end of the day, what you do is just look at all those kind of classification results and take a majority poll. Okay? So you just take a poll at the end. Whoever wins, you decide that's a class. Okay, right? So these are basically ways to divide the, right? So these are basic ways to divide the space of when you're doing classification. So if you want, you can think of the following picture in mind. Right, so let's say you have 3 kind of things. So you have some blue dots, you have some, let's say, red crosses here, and you have another class, let's say, I'm going to draw with green squares. Okay. So you have these 3 classes of points, right? Basically, you're going to classify, let's say, is it blue, red, or green? So what is one against all doing? One against all is basically saying you train different classifier. Basically, you see, is it blue or not blue? So you draw a line this way. Is it red or not red? You draw a line this way. Is it green or not green? You draw a line. Right. Then based on this kind of lines, you determine where your point belongs, which class your point belongs. Okay. And then what is one against one doing is basically saying, well, you look at these two, you're trying to divide these two. You look at this pair, try to divide this pair. You look at this pair, try to divide this pair. And then you're trying to see, based on this kind of division, you try to determine which one of the class this is. Okay. So this, right? So you have multiple classes, they can line this way. Obviously, not one line will work. So you try to divide the space into different chunks, into different pieces, right? And SVM, in some sense, limits you to sort of one such line or one such curve. And really, the classification you want to do here something like this, right? So really the decision boundary you want is some sort of decision boundary like this, right? You separate this into different classes based on one point you pick, you look at which class this is. Okay? So this is the idea of what one you want to get to, but this kind of boundary is actually hard to do within one SVM, right? What SVM is asking us to have a line that separates this kind of things, and here you don't have lines. You may have this sort of complicated, this sort of slightly more complicated regions like this. So you don't have a single line that separates these. Right? And you can have sort of other more complex regions. For example, you can have regions like this. So let's say you have three classes. Let's say this is your blue class somewhere here. And let's say you have a red class that is across here. And then you have a green all around these two. So on the outside. Okay, right? So let's say this is where your points came out to be. And then you want to find some classifier that tell you the blue, red, or green. And there are boundaries you can draw, right? For example, there are ways to separate these classes. You can have a classifier that goes something like this. Right? So you can have a classifier saying, if you fall in this region, it's blue. If you fall in this region, it's red. If you're outside this region, it's green. Okay, so if you have data, you have sort of complex data, it's basically making your classifying regions more complicated, right? So instead of just two classes using a linear classifier, you have more classes, and you may have used for nonlinear classifiers. And this is difficult because before there used to be a lot of sort of creativity of finding out this kind of thing, right? You need to think about what the data looks like and how to classify them, let's say. You rather want a sort of automated machine that you can sort of just crank it through. And automatically you want the classifier to come out this way, basically, right? You want something more automated. Instead of spending a lot of time, you're looking at the data, thinking of different ways to divide them, thinking of the right space to put them in, and doing this kind of sort of manual work. Okay. So before neural networks was really popular, so neural networks has been around for a long time. But before it was popular, what we had was not so much neural networks, but something like ensemble learning. So ensemble learning is a fancy name saying that you train many algorithms and again take the majority poll of many algorithms. This is what ensemble learning means. It's train ensemble of classifiers. This is train many classifiers. For example, you can train SVM. You can have logistic regression. SVM with different kernels. Right, so you train a lot of them, right? On the same data set, you just keep training classifiers using different techniques. And ensemble means you take all of these. When you use it, you look at all of these things, whatever spits out, and again, take a majority poll. Right? Whichever gets the most vote wins as the end. Okay, so we can right, so take a majority poll at the end, and then look at the output that right, so many of this classifier spits out being correct. Okay, so you can view each of the classifier as doing maybe not so good of a job of separating your data, but we have many of them together, they do a better job of separating the data. Okay, so the idea is some classifier will work, right? So if I take a sum of them, idea is, majority of them tend to give you the right thing. So if you just average it out, take a majority poll, those things tend to come out right as, tend to come out. So this is ensemble learning. So before neural networks was really popularized, ensemble learning in some senses, was the best you can do. Just train many, many of them. And you just summarize it by taking a poll idea. This again somehow requires, in some sense, a lot of manual work. You have to go in and train these. You have to tune a bunch of things. And again, depending how good your classifiers are, the output may or may not work so well. Okay. So neural network at least was designed to overcome this kind of problem. Neural network was designed to say, okay, let's just have an automated way of learning classifiers without you have to do any work. You want a computer to do all this work for you without you have to manually specify all these things. Okay. And neural networks has been around for a very long time. Has been around at least since the 60s and 70s. So we'll talk about the basic intuition behind neural network. Then we'll say why it has recently become sort of ubiquitous everywhere. Right. So we'll look at what's the reasoning behind it, why wasn't it used for a long time, and then why is it possible now? Okay. So any questions about that? Okay, so let's start with the basic idea is this is sort of very popular. There are sort of many, many books and courses, right? So we are not going to go too deep into this, but here we're going to look at the XOR example in this class. Okay, so if you want, there's sort of online tutorials, books, everything out there. But for this class, we'll get started by looking at the XOR example. So this is actually a good example. It is a very simple classification problem where linear classifier doesn't work, right? So to remind you what XOR is XOR of x1, x2 is 0. Okay, right? So this XOR, this is a very common logic function, right? So you can think of this as classifier with two inputs. Given x1, x2, classify the output according to this rule. Okay, so this is essentially the simplest, one of the simplest functions you can have. Any question about XOR? Okay, it's just XOR, you have two inputs, you have an output. Okay. So if you draw this out, right, on the graph, as you have, basically it looks like this. You have red here and blue here. So this is 0, 1, 1, 0, 1, 1, 0 there. Okay, right? So you want to classify this, right? So you want to classify this, but the linear classifier doesn't work. So you actually cannot train an SVM to classify this because you cannot draw a line through this data point, right? So how will you classify this then? So let's think about this, right? So neural network in some sense is trying to answer this question. As I cannot separate this four dots, there's two class of dots with one line. And there's some way I can classify this? So if one line doesn't do the job, could I use two lines to do the job? Could I use two lines to do this? Right? Yes, you can use two lines, right? So the idea is, well, SVM in some sense restricts you to use one line. There are things that a single line just will never separate, like this function. So then the question is, hey, maybe I can use two lines. Okay, so how do you use two lines? You can do a classifier this way. You can say, well, let's have a line like this, right? So let's separate your space like this. Let's say anything between these two lines, you classify as one, as red. Anything outside the two lines, you classify as blue. Okay, so this is the idea of classification, right? So you can, if one line doesn't work, have more lines, right? So just add lines until it works. And in fact, that doesn't matter how complicated your classification problem is. You can always break up the plane into small regions. And within each region, you have a single class of points. That's what you can always do. Right? We can always regions, and each region only contain one class, right? So you can make it, right? So even you have more dots, for example, you can make things more complicated. It's okay. You can keep subdividing this plane, right, into more and more linear regions. If your region is small enough, if you use enough lines, you're always guaranteed to do a good job in classification. Okay? You just have, right, at worst, you have each point, it's its own single region. You can always classify. Okay, right? So yes, any question about this? So now the trick comes is, if you have two lines, as now it seems to be a lot of work to break up this region into different lines, right? So even in SVM, we have one line, we can optimize over one line. Now, when you have many, many lines, you're breaking up this region into smaller and smaller pieces. And it seems to be able to do a lot of work. You have to write down a lot of linear equations. You have to break into many lines. You have to write a lot of if-then statements, right? So this classifier basically is an if-then statement. If it's in this region, it's 1. If outside this region, it's 0. If-then statements are not easy to work with, right? It's not continuous. It's finding the weights is difficult. And this goes back to some of the, if you think about the one against all, the one against all or one against one, the problem with those kind of classifiers. As you don't want to say, oh, let's look at this line individually, and then look at this line individually, and look at what happens there. Okay. So the trick is now, if you look at this XOR function, is there a way to write XOR into another function where you can avoid this kind of if-then statement? Right, so the trick is, can I write this into a function that I don't need this kind of logic statement to show up? I just want continuous functions, but without logical statements. So that's a trick. So that's, once you get that trick, neural network basically built on that trick. Okay, writing if-then. As you can think of as a trick of, you want really if-then statements, but right, you want if-then statements, but you want to do it without this for logic functions. Okay. So let's think of the simple thing first. So the question is, can we do logic? Right. So we want to do this as, at the end of the day, when you're doing optimization, when you're doing training, you want to do derivatives. You want to take derivative of things. Okay. If you have if-then statements, I can't take derivatives. Okay. So here the code is, can I take a derivative? Or can I basically can I take a derivative, but still in core logic. So let's look at a simple example. Okay, so let's say I have a very simple function. Okay, let's say the not. Right, look at the not gate. Okay, right? So this is even a simpler function XOR. This is not X. So what is this? This is 0 if X equals to 1, 1 if X equals to 0. Okay. Can you write this as a function now? The question. Can I write this not X as f of X, where you just use addition, subtraction, multiplication, function evaluation without this if statement? Can you do that? Okay. X minus 1 in absolute. That works. That works, right? So that's a good suggestion. Right? One suggestion is, for example, not of X equals to X minus 1 in absolute values. Right? So this is one suggestion. If you plug in 1, this is 0. If you're plugging 0, this is 1. Okay, so this is good, but can you do better? Because absolute value seems to be, it's hard to build this up, right? So this can seem to be a strange, a little bit too specialized of a function. Right, so okay, so now let's look at another, right? So you can have a better function as this is not of X equal to 1 minus X, right? So this works. Okay, so this is a way to say not X is actually equivalent to a linear function. Okay, so I can do logic. I can do this logic with just this linear function. Okay, so if you have this is in some sense the simplest classification you can do. Right? So instead of doing this, learning this logical function, you can just learn a linear function. If you get this linear function correct, you can do this logic. Okay, so a classification you can think of just many sort of logic elements chained together. Okay, so this gives you some hint that your functions, you don't need this if then, you just need a linear function. So now let's look at a harder example, basically XOR. Okay, so we did the not function. How about XOR? Again, this is 0 if x1, right? 1 otherwise. Okay. Any suggestions how you write this? Some function without this, right? Can you write this? So the trick is to avoid absolute value, because absolute value will have the problem of not giving you a negative number. Right? So you want to square is not good because square doesn't divide the region into little pieces. Right? So you want a way to divide region into little pieces and where you can still do logic. So square is too complicated, not good. Square blows things up. So the trick here is to recognize there is one function that's very useful. There's called this ReLU function. Okay, so this is called rectified linear unit. This is nothing but a fancy name for this. Okay. So if you're engineer, electrical engineer, this is just a dial. Right? This is just a dial. This basically, this is a dial, right? If the input less than 0, it's 0. If it's more than 0, it just takes this function. Okay. So this is this equation. Okay. And the intuition for the neural network is actually goes back, if you want, goes back to electrical engineering days, to say that any logic can be represented by linear functions, by addition, subtraction, multiplication, and using dials. That's basically, this is a theorem goes far back into, when we just had dials without transistors. This says, okay, so question is using this dial, right, ReLU function, can write XOR. Okay, so there's a simple way to write XOR using just a ReLU function. You can think of XOR two times ReLU x1 plus x2 minus 1 there. Okay, so this is a way to write XOR. You plug in 0, everything is 0. You plug in 1, this is 2, this is 2. This is evaluated out to be 0. You plug in one of them is 1, one of them is 0, this comes out to be 1. Okay, so this is, you can check where this function works. So this, you can check this function works. So this is the way to, what this does is basically this breaks up the plane into different parts. What this does is breaks up the plane into precisely the way we want it. Okay, so what this function does is, so and be consistent. You want to classify this way. Right? So what does this function do? This function basically does something like this. Okay. This is a nonlinear function. So you can encode many linear constraints. You can encode many linear inequalities in this one function. And what it does is uses a dial logic here, and to say that you can realize more complicated logic if you just have linear operations plus a dial. Okay, you can encode complicated things, very complicated logic if you just allow very simple operations, linear plus one diode operation. Okay. And this is a useful function to have because you can actually have a following proof. You're having the following proof. You can have the theorem you can have is to say that any function, quote unquote, so this is not any, but let's say reasonable functions right? So reasonable functions f of x1, x2, xn can be represented by by functions composed of linear operators and diodes. Right, this is real. Okay. So what this does is just you take any most reasonable function, reasonable meaning any function that you can think of, functions you can think of. So you can read this as most functions. What you can do is you can represent if you have enough linear operations. You have enough linear operations, and all you need is this one nonlinearity. All you need is this one nonlinearity, and then you can represent whatever function you want. Okay, so this is basically the inner theoretical result, underpinning some of this neural network. It says, however complicated your decision function is, there is a way to represent your function using very, very simple elements, right? Using just linear operations plus a single nonlinear function is enough. Okay, you give me enough of these building blocks, I can represent a very, very complicated function. Okay, so this really is what neural networks trying to do. Okay, so it's to say that how do I represent a complicated function which you don't know by simple elements? Then the theorem says if you have enough elements, if you have enough this elements, linear operations and ReLU activation functions, you can represent whatever function you want. This is basically the so-called universal approximation. So this turns out to be actually a fairly easy theorem to prove. This is not a magical theorem. This doesn't really take much to prove this. Any idea of how you would go about proving this kind of thing? So you say, I gave you a complicated function. I want to say, okay, now let's approximate this complicated function. And my claim is this sort of linear operations plus this sort of max there, x and 0 will do it. So this is actually quite not all that hard. I mean, so to get it technically correct, of course, you have to use some function analysis here. But to get it, get an intuition about this is actually not very complicated. Any ideas how you go about proving this? Anybody who remember calculus? So if you take a function, for example, you can do a Taylor expansion anywhere, right? So what is Taylor expansion trying to do? What does a Taylor expansion do? Approximation with what? Right, so if I take a Taylor expansion and I just keep the first linear term, what that Taylor expansion does is I'm going to approximate your function into a linear function, right? As a Taylor expansion does. And Taylor expansion works if you don't deviate from the point where you're doing this expansion enough, right? So Taylor expansion is good if you look across a small region, look at a small region where you're doing the Taylor expansion. So this neural network is basically doing the same thing. It says if I subdivide this region fine enough, what I get is that you're basically look at linear approximations of your function at all points. Okay, so what this theorem basically does is you can think of one-dimensional case. Let's say you have this function. Right? So I want to approximate this function. What I can do is I can approximate this function by looking at linear pieces of this function. I can have a very fine linear piece around this function. Right, so I can fit this sort of function into the sort of linear small pieces. Right, and if you look at each region, what this is a linear function on a linear piece. Right? So you have a linear piece. You look at some small linear piece. This is the approximate linear function. You can do this. You can approximate any sort of most, I guess, Lipschitz continuous functions this way. And you can imagine the two components of this. You can think of this max of the x at 0 dividing up the space into small linear pieces. Okay, so this is basically what this max 0 is doing. It's dividing your space into this sort of little chunks of small pieces. Then on top of each piece, you just use a linear approximation. Okay, right? So this is basically what max x of 0 is doing. As you subdivide the region. If you subdivide fine enough, every function looks linear. So for that region, just have linear functions. Right? And then you can assemble this whole thing together and you approximate a function well. You can approximate most functions well. This is basically the idea of why you can use so-called neural networks. As any function, in principle, I can write it this way. And then the hope is I can get a computer to find, how exactly is this division done? Crank the knob, get a computer to do this. Each region, what is the best linear fit? Crank the knob, get a computer to do this. And then at the end of the day, any function that you want to learn from data can be learned from assembling the small pieces. This is the idea of why neural networks, people have some hope for neural networks. Okay. This is not how your brain works, right? Your neurons doesn't have to work this way. It's not so much, we want to build a machine that's assemble your neurons. Who knows? But we don't know how we're not quite sure how human brains work. May not be something like this. The idea is basically just have enough pieces of simple things, you assemble them together, you can approximate complicated functions. So like human neurons, each neuron is relatively simple. You just have a lot of them. And by the collective action, you can do complicated stuff. Here, the same thing. You have simple pieces, you build them up, and together they can do complicated things. Okay? And here is, so we don't have to use ReLU. There's many other functions. There's many other functions. There are sigmoids, there's soft ReLU, leaky ReLU, whatever you want. They basically all work this way. You have linear operations plus some sort of simple nonlinearities. And then you just assemble them, enough them together, they can approximate many functions, right? They can approximate essentially whatever you want. Okay, so any questions about this intuition? Okay, so when we use it, of course, you're not going to do any of this, right? So this is now been essentially, it's not really an art anymore. Now this is just your computer got very good at doing this. But neural networks nowadays is again built up upon this idea. Still that if you take a classifier, what you do is you basically put X, you put into through a linear operation, you put into some nonlinear function, and then you repeat, and you get Y. This is the process, right? So each time, as you have linear operation plus nonlinear things, you can think of this as dividing the space. You do this many layers. You subdivide the space finer and finer, and then the day you can get some output Y. Okay, this is how you build a neural network. And drawing this out a bit more, as you again, so in representation, you can think of this as you have this is called a neuron. This is your computational unit. There's some function that takes a linear combination of your input and get something out of it. Right? So this is x1. Okay. And this is how we connect the unit. Right? So this is how we think of each unit. Right? So this f, again, for example, you can think of this as a ReLU activation function we have. Right? You take again linear plus nonlinear functions. You do those things in many layers. And the neural network part is just that you will connect this into a network feature. Right, for example, we're going to connect all these things together. So you have 3 inputs. Okay. So each of these lines are some weights, right? Each of these are activation functions. And the Y you get is your output. You can have output as your Y. Right. So your computer basically, what is when you train a neural network, what is it doing? It's basically finding this weight. Okay, saying I'm crank this through. I'm trying to find the weights that makes the output good. Right, that makes the classification error small. And by looking at this weights, right, so you keep doing this until you think you get a good set of weights. And then when you use this in practice, classify, you just put in some numbers here, and everything just propagate forward through this network. And you can get a Y at the output. Okay. So this y in general is a real number because again you're doing linear operations, right? You're using real numbers. But to make it into sort of classifier, this is very easy, right? So this is, you think about classifying handwritten digits. This is basically how this is how it works. Is you have a image, right, with different inputs, right? So this is a pixelated image. What you do is you put this through a neural network, right? So you put through this through, right? So this is, right? So this is 16 by 16. This is 256. You have many, many X in your input. This thing goes through many, many layers. And output, you basically have Y0 to Y9. Okay, so your output, so neural network has no concern about how many output it has. It's basically just functions. You propagate through. So you have, when you have a handwritten digit, you have, let's say, 9 of them, right? You have 10 possibilities, right? Oh yes, you always have multiple information. Almost always, right? So remember this thing is 256 pixels, right? So this length of this thing is 256. You put every pixel as one component of X to shove it into the neural network. And outcome is 10, 10 outputs or label from 0 to 9. Right? So what are these outputs? Right? So these are the, right? So this, for example, possible image, let's say this is the 8, right? I write. So here what this does is Y0 to Y9. This is a relative likelihood of 0 to 9. Right? So basically the way this works is you read out you figure out which one is the highest and just say that's the classification decision you make. Okay, so you have 10 possible alphas, 10 real numbers. One of them will be larger than the others. You pick the largest one, you say that corresponds to your input. For example, here, Y8 is the largest, say, output is 8. Okay, so this is your neural network. Okay, right, so you just have input, you have again 256 pixels, all of them, put them into a vector, all of them goes into the network. This neural network will crank this thing through, and that will give you some output, and your output is, right, 10 of them, pick the highest one, that's how you classify. Any questions about this? We train, right? After we train, right? So the main challenge with neural network and why it wasn't used is, how do you train this, right? So it's not, right? So imagine how many, parameters SVM has. Not that many. It's just one linear function. Look at how many parameters this thing has. Lots and lots and lots of, right? So if you look at something like ChatGPT is what? Some trillion number of parameters, right? Some like, it takes you a month to train, right? So that, that many parameters. Right? So nowadays, these large language model, the large part of the large language model, this thing have trillions of parameters you train. Right? So you are not going to train that on your computer, but somebody can train that, and that's your model. Even for a relatively simple model like this, it's not uncommon to have millions of parameters. Okay, but assume this can be trained. That's much easier to use because your output, you can specify your output to give you whatever you want. Right? That's much, much easier than use them to say, let's train a bunch of SVM. And the fact that you have a lot of parameters in some sense nuts, right? Because you have a lot of parameters, I can really subdivide the space really, really fun. I can have a lot of parameters that can divide the space into really, really fun regions. And then that allows me to learn very, very well. Yeah, right? So we have, large language models, This is saying I need some trillions of numbers of parameters to generate reasonably looking sentences, right? Okay. So in this class, we're not going to worry about how to train this. This is the own topic. Why? How do you train neural networks? Why does it even work, right? What is it going on? Why does it even work? We're not going to worry too much about that. We're just saying for anything you likely to see, this works. Okay. So in fact, connecting to energy is, if you train something with a trillion parameters, how much power does that consume? Let's say you're training a large language model. And people will say, oh, training this thing costs millions of dollars. That cost is basically power cost. As you have to pay a bill to train that. That's your power bill, $10 million for training that. So how much power do you think that's roughly corresponding to training one model like this? Right, so it's 1 megawatt, right? The question is megawatt for how long, right? So typically training this kind of models, will power a city size of Seattle for a good few days, actually. Like that's the amount of power goes into it. And to train that model, this goes in some data center, it just runs. And sometime later, it will spit out, these are the training parameters that you have. And to train that is not insignificant amount of power cost. So notice if you run your data center, actually for most data centers, the interesting thing is that computing your server cost is very cheap. Servers are dirt cheap, right? What is not cheap is power. So that's why you build data centers along rivers. You directly build a dam beside your data center, and it's hydropower to power them. Or you build a data center somewhere in Colorado because usually it's cool. You open the doors, there's no walls, and you can do air cooling, and you can cool data centers. You don't have power bills for cooling data centers. But anyways, the thing about neural networks interesting is training, we're somehow moving from kind of do the computation. How many computation do I need to do to train a neural network? Nowadays, we're moving from what is the cost of training a neural network? Cost is translated from power cost. What is the power bill in training this neural network? And these things are not cheap, right? So these things are not cheap. Okay? So again, in our campus, we have sort of clusters that you can use to train this kind of things. You pay some money to use that cluster. A small part of that money goes to IT maintenance around the cluster. A relatively large fraction goes to the power bill this cluster is consumed. You're basically paying the power bill. And in this building, we actually have people who bring their own servers into the building for machine learning, for network training. Building managers not happy with this. Because if you train this, actually you see the power spike is actually not great for the transformers we have. Okay, so power is actually becoming an issue here. But for us, for training neural networks, it's suffice to think of this just multiple, right? So this sort of high dimension input goes in, possibly high dimension output comes out, right? And we'll do sort of, right? So we'll do a few things and we'll look at more detailed examples, but let's look at a few things first. As you have a neural network structure, and this structure is basically specified by many things. The structure is a topology. This is how many layers. How many neurons per layer? And topology, and this is weights, right? So what are the weights? What are the weights you have between different layers? Right. So you can say, oh, I have something that's 2-layer neural network. Each layer has 50 neurons. You can have something with 100 layers, and each layer has 1,000 neurons. So there are people who work Microsoft, for example, that has neural networks with few hundred layers. Each layer has few thousand neurons. Nothing again takes you about a week to train their infrastructure. And so training can take some time. But a lot of times what you do when you're working with neural network is your menu job is basically select this. So this is called hyperparameter, right? So this is called a right? So weights, this is trained automatically by computer, right? But hyperparameters are selected manually. Okay? So if you work on neural networks in real applications, most of your time is selecting this. You have to tell the computer how many layers do I want, how many neurons per layer, what kind of architecture I want. Then it's automatic. Then you're not very unlikely you're coding actually the optimization back here. What you're doing is you're selecting this kind of things. You give it to the computer and say, go with it. Find me the best weights. And the weights is trained by something called basically by propagation algorithm. Okay, so what the weight is, weights are found by minimizing. And the error is a very standard error. Your loss function, this is right. So this is a extremely standard error. Is you have prediction, you have your label, then you update the weight to minimize this error. And this is then basically the algorithm is a clever way of doing derivatives. Okay, right? So it's based this ways you want to find the derivative of this loss function so with respect to the weights. And the algorithm basically is how do I do this? How do I find this derivative? And the key sort of back end of neural network training is there's a very clever way of doing very fast derivatives, of doing essentially almost sort of symbolic computation of derivatives. You're not taking a function and doing derivatives. You're basically at the back end is there's quite clever way of fixing some things and doing derivatives extremely fast without storing many numbers, without doing a lot of computations. It is unclear why this works. It's unclear even if you're doing something, if you're actually doing derivatives or not. Because if you look at the basic function, right, this ReLU function, right, so this is using a lot of neural networks. Nothing is not differentiable. Right? You have this sort of step here. This is not differentiable. There's no derivative at this point. Right? So this part is differentiable. This part is differentiable. This point is not differentiable. So this whole function is actually not differentiable. But the some of the mystery is that ignore the fact this is not differentiable, pretend there's a derivative, do that in some ways, and turns out things work at the end. So if you're doing if you're doing theory, machine learning research, a big part is why does this training work? If you're doing applied work, which most of you will be doing more applied work, is you're basically in this space as you're tuning hyperparameters. And this is a little bit of art. Like, how do you tune this? What is the right architecture select? Take some experience. And if you tune, whether you're good or bad at doing this, if you're very good at doing this, you can make a lot of money. You're very good at tuning this parameter. There's some people who's very good at tuning parameters, some people who's not very good at tuning parameters. But that's sort of if you go out and work with neural network, this is where most of your time is spent. Everything else, as you type it in, it's still one line. These things shows up as hyperparameters. You put it in, you press enter, or just go and train. Still one line command. Okay. Questions about this? Okay, so we'll take a break. Then afterwards, we'll look at some sort of, pretty pictures and examples of how this thing works. Okay, so let's take a 5-minute break, then we'll look at some more examples. Better pictures than I can draw of how neural networks work. But before that, to recognize that neural networks really has been around for a very, very long. Right? So the math behind it is not very complicated. But really, the problem has been that their application used to be very niche, used to be very, very niche. Actually, when this building was first constructed, so this building was built in the 1990s, we actually used a neural network for some operation in the building. Can you guess which one? We don't use that now, but when we first built this building, people are doing neural network research. So I thought, oh, we'll try something in this building. This is what Mohammed Ashikawi, who's a late professor in our department, told me. Can you think of which operation in the building require a neural network? So in one sense, it's simple enough. Your computer in the 90s can train this neural network. But in other sense, it's confident enough that you don't want to manually deal with it. Right? No, not security. Right, so this trying to say that neural network has been a very long time, but the application is very niche. Used to be used for very, you can think of weird applications. So one example was the application in this building. Something in this building was driven using a neural network. Can I think of what? So what in this building seems to require a bit of logic, right? So it's more complicated than turning the lights on and off. That you don't need neural network, right? It requires sort of a bit of logic, but it's not super complicated. Right? So that was an elevator operation. Our elevator is driven by neural network. The reason that depending where the elevator should go, depending how you press, where it should go first, that was actually a neural network back to the elevator. And in that time, that was sort of the only application people had, at least in EE. It's okay, that's what neural network does. It's useful for driving things like elevators, which is simple, but somewhat tedious for humans to figure out, right? And the reason for that being true is neural network really took a lot of computational power to train. You have to do a lot of derivatives, and you have to compute these derivatives many, many times to update the weights. It takes a long time to train. So at that time, a two-layer network, right, with sort of not many neurons, was not doable. You couldn't train it. Okay? And right, so if you think of the computing power from the late 80s, early 90s to now, computing power has grown by I don't know how many times, right? Trillion times or something. And that really allowed us to train neural networks that's much, much larger. Okay, so this thing used to take, your biggest computers around, two-layer neural network took it a week to train. Nowadays on your personal laptop, even on your phone, you can train. Right? So really it's because of computational growth. Like just the fact that we can compute things many, many times over is nowadays you have language model that's hundreds of layers deep. Right? Training one neural network like that required, more computation in all the computing in the 1990s had. Right? So it just comes from the growth of computation. Right? Really, the bottleneck here was computation. Nowadays we have solved that bottleneck. Now the bottleneck of the neural network a lot of times to come down to actually power, cost of power. You can't, it's too costly to train. And the cost is not buying computers, the cost was can I have enough power supply to the computers to train it, right? So this is where the thing is today. Right? So to give you a bit more sort of fancier picture of what neural network is doing, it's basically you can think of this neural network as twisting the space in some sense. Okay, so this neural network is twisting the space, right? So this is actually a real example of saying things like, okay, Blue and red are sort of two functions I want to separate. Okay, so I want to separate blue and red. Right? There's no linear separators that you can have for blue and red. Basically, you cannot draw a line that completely separates these two curves. That's not possible, right? So this is sort of the best line you can draw, but still get some parts of this curves wrong. Okay, so what can you do? Well, after this sort of first hidden layer, right? So this is a nonlinear function. What it's doing is basically twisting your coordinate system. Okay, so what it's doing is I'm gonna now twist this coordinate system into this sort of weird coordinate, basically, right? You're going through a nonlinear transformation. So your squares become this sort of, not so square shapes. Your blue line looks like this, your red line looks like this. And now you say, oh, now you can draw an easy linear separator. Okay, in this new coordinate space, you can draw this linear separator that separates two curves. And then at the output, what you can do is you can transform this back into the original space. When you transform back into the original space, of course, the blue and red curves doesn't change. What does change is this your linear separator now becomes a nonlinear separator. And this is the way you can separate these two class of functions. Okay, so nonlinearity persists into a new sort of space. You can think of some new space. Draw a linear separator in this new space, simpler separate in this new space, classify in this new space, turn it back, and now you have a nonlinear separator. You suddenly have a nonlinear separator. Okay. Questions with this pictures? So you can think of this hidden layer, right? This sort of intermediate layer is called hidden layer. What's doing is sort of twisting and turning your coordinate system, making this kind of transformation, right? So you're not quite, again, you're not entirely sure what is the transformation actually is, but you can think of as finding some space where a linear separator works. Okay, so your weights are all linear, right? These are all linear. So you're still trying to do the linear separation, except you're in a space where it's easier to do linear separation. Questions with this? Okay, so this is doing, so you have many layers, you're basically twisting and turning this a lot, right? So one transformation doesn't work, keep transforming it, keep separating, eventually, hopefully things work at the end. Okay, so we cannot visualize, of course, more than two, it's hard to visualize more than two dimensions, but if you want, you can think of this way. Or you can think of, okay, this nonlinear separator can be approximated by linear ones, and these two are just building up this nonlinear separator. So all this intuition works, right? Questions? Okay. So that's the separators, right? So of course, when you have a deep neural network, right? So you just stack layers together, right? So you do have many layers. So if you have, for example, hundreds of layers, the question is, what is all these layers doing, right? So why have 100 layers? Well, why, deep neural network means the deeper something, the better. Again, when you have language models, you have very deep networks. What are they actually doing? Why do I need many layers? So there's some intuition on what's doing, but again, this is definitely not a sort of complete idea. So the intuition is the following, is to say that if you look at many layers, deep neural networks, you can think of, let's say I input an image and go through many layers. This is post hoc. This is after you train the neural network. You look at sort of intermediate layers and you give some interpretation of what's going on, right? So we're not designing the neural network specific for this, but this is afterwards, you try to interpret what's going on. So after you train, you input some image. What you tend to observe is the first layer was so-called is take out this low-level features. So these are things, is it mostly green? Is it mostly blue? There is this sort of solid color, this stripes going on. So the first layer after training, you can see there's not much details here. This is called low-level features. So a very coarse view of the picture. Go up one layer, this pick up a bit more detail. And this will give you a finer grain view of what the picture is. And then you keep going up in layers, and sort of try to pick out more and more details in your picture. So one intuition, the idea is the more layers you have, basically the more detail you can extract. So the first few layers are just looking at sort of broad strokes of the picture. And then mostly white is mostly black, and there's different colors. Then the fun details gets extracted by higher feature layers. Okay, this gets extracted by higher feature layers. And because you're separating out this feature extraction, more and more layers, of course, you can do better and better. You can add this into this feature extraction. And so, and then at the output, you recombine them, right? So when you're doing classification, some classification maybe it should be done in the low-level features. Some classification may be better done at the high-level features, right? So again, the classic example is if you have a picture and to classify is it a dog or a cat, then maybe low level is not so useful. There's some sort of animal, but middle features may be more useful. When to classify what kind of dog it is, maybe you want very high level features, very detailed. When to classify something as a human, as a human or a car, it may be enough just to look at the shapes. You don't need very high level features. So this is, in some sense, you're trying to say a neural network is doing this automatically, right? It's doing this thing automatically. Okay. And so the similar idea is you have sort of large language, we have language models. And you're saying, I'm going to put this whole paragraph into the neural network. What is it doing? I'm going to say, okay, it's trying to extract meaning from this paragraph, right? The sort of broad meaning of the paragraph, that's a detailed word structure. And we have more layers, you can pick out all this more detail. You can combine these different features, reassemble them, and get something that sort of resembles real language. Okay, so this is this is a post-hoc interpretation. We don't go in and thinking, oh, I want first layer to do this, second layer to do this, third layer to do this. You go in and say, I'm going to train this neural network to get the best classification performance. And afterwards, you sort of see this kind of extraction. You sort of interpret things this way. Okay, questions about this? Yeah. Okay, so what in power system user extraction get? Okay, so I'll give you two examples. One is actually coming from a language model that was used for power system. I'll give you sort of more physics-based power system example. So language model is something that I have worked on. So for example, so this is trying to understand parallelisms, it's basically. So Seattle and almost every utility has a lot of power outages. So when you have a power outage, what you have is you have a log associated with each power outage. So whenever there's a power outage, a log is created based on the power outage. And within that log, essentially a lot of times a free text description of what happened. So somebody say this power outage happened at this time, an engineer went to this street, walked around in the street, observed a tree fell down on the power line, and took the following steps in computing on sort of restoring power. That's one example. For example, so city light, every power outage will have this log. So what we have is we have logs, and this is free text. Right? So X went to outage, walked around, observed Y, tried X to fix it. Didn't work. Called. This is actually a lot of log goes this way. It's just somebody describing what they did. Right? So you engineer, you say I did this following thing. Okay, so somehow we ended up with like a lot of logs. Each outage have a lot of sentences written associated with them. And there's this big pile of free text that's been built up in Seattle for the last 40 years. So now we want to, let's say, understand outages better. Right? We want better forecast of how long they last. We want to do better cost detection. We want to see how do we shorten outage time, how to reduce outage, and so on. Your most information actually are containing this kind of sentences. So it's impractical for a engineer, for a human to read through them. It's actually impractical because it's hard to tell the human what you want them to do when they read this kind of language, right? Just somebody wrote this, what human can read it, but it's hard to extract information. So one way where we use this sort of neural network with quite fancy neural networks at that time is reading years and years of log like this, extracting different features, extracting sort of what is important, predicting outage time, right? So if you just have so this log is hard to read because some part of the sentence is completely useless. The fact that who went to this outage is not very important. There's some engineer that went to the outage is not all that important, right? What you observed is very important, right? So when you try to fix it is also important. The fact that it didn't work is important. Who you call is typically called supervisor, not too important. Right? So there's a lot of this information hitting this language. It's very hard for humans to code up something to process it. So what we did is we basically got a language model, process all these logs, and that's nowadays much more actionable. So if you have now the engineers today have a question to say, look at this location in the network, is it more likely to have outages? What did we do in the past to fix these outages? How long did it take? We can look at the process information extracted from this language model and directly work with that. Instead, before what the engineer has to do is you basically do control F and try to manually read through all these logs and try to process that. That was very costly. That cost a lot of human time. Nowadays, they can ask the question directly, we'll process its words, and we'll tell them sort of the relevant information. So this is a application of the language model in a processing context. Questions about this example? Good. So how do we extract the features? Okay, so you basically get some network like this, except it's more complicated than this. So you're familiar with attention? Have you ever heard of that word? Attention network? Okay, so the challenge with reading language, reading human language, the challenge is a lot of sentences are very long, and they don't make a lot of sense until you get to the end. Right? So a lot of times in natural language is you have the subjunctive in the first part of the sentence. You read. Whatever happens, the important part is actually at the very end of the sentence. You have those kind of language structures, right? So you have to read this entire paragraph to know what's going on. And the problem with the neural network is, well, if you input a sentence in this sort of, in one direction, it may not remember what was said in the beginning. And neural network says there's a lot of words that I don't remember what's going on in this long sentence or long paragraph. So the way you do this is you actually train two neural networks. One reads the sentence from the beginning, one reads from the end. And then you read from both directions. You see the keywords that sort of that explain this sentence when you read from both directions. And then when they both select, they basically, if you read from two directions, you can pick out the important keywords. And you can start building your features that way. To understand, basically trying to ask the question, to understand this sentence, which are the words I need to know? if we read from both ends. Right? What are the important words that both now start to make sense? And then you build on top of that. Right? So this is called attention, is you want to extract the important part of the sentence, important information of the sentence. Right, right, yeah, right, yeah. Something like this going on, right? So you can think of, if you read a sentence like this, your first thought typically goes to, there was an outage. That's actually what I read. Is this sentence describing an outage where this guy saying, I walked around for 2 hours, I went to lunch? Like that happens in the walk, right? So this describing an outage, or do I have to ignore it? So there's the outage. You can extract more as, oh, I tried this to fix it, but it didn't work. You can extract more as, who do you call, this kind of thing. So you do have this kind of sort of significant, less significant, you can build up this kind of different layers of features, even in your sentence structure. Slightly more complicated than that, but you can think of that. Slightly more complicated than that, yeah. Because it's, again, a lot of times this relationship between words, right? You say, this did not work. And then figure out what is this referring to, right? What did not work? Right. So this may be something very far away from this thing did not work. You have to figure all these things out. But essentially, you can think of sort of capturing key information in a sentence. Right? The challenge with a sentence is like, this part did not work, maybe very, very far away from what exactly did they try. Right. So you have to figure all this out. Right. So it's not trivial for a sentence. But it does work, right? So it's basically you train this network, you tune it a lot, and eventually the thing works. Okay, all right. So okay, good. So this is a language model application. You can have more physics-based application. You can say what you're trying to do is you're trying to detect instabilities. So what instability does is, so if you measure something like this is time. And then what typically we measure is frequency in a power system. So a normal looking frequency is 60 hertz, right? So in North America, if you measure the frequency of the system, is roughly around 60 hertz. It doesn't vary all that much. So you have this sort of small variations around 60 hertz. Now, an important question is, if you see, sometimes you see this sort of large oscillation starts to happen. And then your question is, what happens now, right? So your question is, will this eventually get damped down? Like the system will recover to 60 hertz, or the system just blows up on you? Okay, so this is an important question you ask as a system operator. Right? So nowadays, the way we do this is actually a manual detection. So if your oscillation is large enough, a real alarm sounds, and the operator looks at it and makes a decision. Whether it's stable or not stable. If it's not stable, you press this button and it shuts down some load. That's basically what you do. And that, you're putting a lot of pressure on human operator. They don't always make the right decision, right? There's sort of limit on how fast humans can process information. Okay. But nowadays, the goal is to do the following: so when humans look at frequency, they basically look at frequency at one particular bus or an average frequency in the system. What information nowadays we have is we have at every bus, you have something like this. You have some frequency oscillation, some larger, some smaller, some bus maybe doesn't do anything. You have many, many buses. You have all the sort of measurements coming in. You can think of this actually as an image. You have a network. Each node in the network is a pixel you have. In each pixel, you have this sort of time domain traces. Now you're asking question is, given this sort of image, or you can think as a movie playing forward, tell me, will the system be stable or unstable? Tell me this information. Okay. Extract this information for me. Okay, so you have let's say you have a some network. like this. So at each of nodes, you have this sort of time domain oscillations. You collect all this information. You want to decide, do I need to do anything? Is the system stable? Is it not? If not, what do I do? Okay, so this is a very challenging learning problem we have, right? The challenge comes from is one, real systems. Right, so real systems have larger than 10,000 buses. Okay, so you have 10,000, right? You have a picture, with 10,000 pixels. Each pixel is actually a function. You're measuring this oscillation. You get all these things together. I want you to decide in, let's say, 100 milliseconds, yes or no, the system is stable or not. Right? So this is, right? So to do this, again, you need a pretty big neural network to do this. And what you want to do is you want to extract the right information. Okay, all of this, there's too much information in this. You have 10,000 times however measurements you have per trace. So you want to extract information. You want to say, okay, where is the fault, right? Can you isolate the fault? Most of the oscillation in the system are not really relevant. There are sort of few modes you care about. You want to get those informations out. You want to do this sort of, levels of refinement in your information extraction. This is the hope of how machine learning can be used in the power system. Right? It just basically give you massive amount of information. This really, you can think of a place like a movie. You just have frames. Each frame is a huge picture with 10,000 pixels. It's a frame by frame play. You look at all these frames, you try to predict what happens. What happens next. Okay. So this is a hard problem. I don't think anybody has a solution to this yet. This is fairly challenging. It's a fairly challenging problem, both from a theory perspective. We don't really understand large nonlinear systems all that well, and it's not clear what is the right tool to use for this. Okay. Right, so the good thing to think about is this classification problem, this thing, stable or not. This is in some sense, very different learning problem than a large language model. So why is this different? Any ideas of why this is different? There seems to be, related, right? You just a lot of data, right? You just all have a lot of data. Language models have even, way more data than this. You want to train it to do something, right? Nowadays you can have language model that writes poems. Why can we not use it to detect what will happen in the grid? Grid or not, there's no humans, right? This is purely physics problem. How hard can it be? Why is language modeling something simpler than this problem? Right, so the main problem is grid is stable vast amount of time. Grid is not, right? So, every year in the US, we may have 2 examples of the grid not being stable, and the operator needs to take some action. Right, so we're seeing more and more. We're definitely seeing more and more. Now operators are taking a lot more actions. But even that, 99.999% of the time, the grid is stable. The very little percent of the time, the grid is not stable. Where you have a large language model, what it's doing is giving you something reasonable, right? Just giving you something that sort of looks like a human wrote it. So it's very easy to give you something that looks like a grid response. That is very, very easy. It's very hard to find this sort of needle in the haystack. Really identify what does not stable look like. Right? How do you detect small signals that will lead to things being unstable? That is very difficult. That is a hugely challenging problem. That's a lot of research is done in this area. Right? So definitely I work hard on this area, but that's another application. This is sort of, and both of these applications are quite difficult. Like the machine learning, the neural network model construction in both of these is considered for state of the art. This is where you do this kind of research, you actually need to have a good understanding from how do you construct this kind of models. You can't, off-the-shelf tools doesn't really work for this one or for this one. You have to do a lot of work on your own. But for most industry applications, off-the-shelf tools will work. They work pretty well. Right? So unlikely you're doing this kind of analysis. Right? So industry work, you may have things like you're not doing this kind of instability detection. You're looking at is there electricity theft? That you can run neural net machine learning on. That detection actually works very well. And it's a relatively easy problem to detect, is there theft in my network? Is it inefficient operation or is there theft? Is there measurement there? That machine learning works. For stability, this kind of question, we're sort of not close to understanding what to do here. So this is a problem where human-based, detection tool, human-based detection or purely first principle driven detection doesn't work. It's way too, you have too much data, you have to make decisions in too little time. So that doesn't work. So you should have some, learning would help. You would think learning would help. It just is a hard learning problem. It's a very hard training problem. Right? Mostly because you don't have enough data. You just don't. Okay. So if you just train a neural network, will tell you things are just stable. And you're right 99.99% of the time. So neural network thinks I'm doing a great job classifying, which is essentially useless as a classifier for you. So that's where part of challenge comes. Good. Yeah. No, stabilizer is not. Stabilizer is a PI control tool, PI controller, not a generator, not tuned by humans. Now we don't know how to. That is related. It's related because we're not very good at guaranteeing a machine will actually tune it to stabilize the system. So you have a human to tune it. But so that's human tune. Right? So it'd be good to have a machine learning tool that can tune it. But whenever you're looking at stability, you need to prove stuff for it to be used in practice. And these proofs are very hard to get. Right? It's very hard to get a proof. This thing works. But whereas humans, you can blame the human. Right? This guy will go to jail if this is not stable. Right? You're not going to blame machine learning. Right? So that's human thing. Right? But there's more and more this sort of hard problems that's showing up in the grid. It's a very hard problem. Any other questions about this? Okay, so we'll finish by looking at some examples, right? So, for example, convolution neural network, we're talking about features. This is the way to extract features, right? So this is really used for images. What used for images, right? So for images, what people observe is basically there's sort of multiple skills going on, right? People observe things close to each other tend to look similar. Things far away tend to look different. So convolution just says, let me do a low-pass filter, in essence. Let me do a low-pass filter so I can detect things better. And the good application for this is actually edge detection. So you can ignore, we don't need to look at that as edge detection. Okay. So edge detection means the following. As let's say you have an array of data like this. So 0 and 1, you can think of this black and white. What you want to do is you want to detect the edge between different pixels. Okay, you want to know where the edge is. And edge detection is a fundamental problem in image recognition, right? So, whether there's a human walking across the street, you're basically doing edge detection. Is there a human? Can I detect the edge transition between two different objects, right? So you're doing edge detection. So this is one problem. Right? So edge detection, how do you do edge detection? So any ideas actually from you guys? How to do edge detection? Right? So again, guy walking across the street, you have a picture with different things, there's the edge between them. How do you know where this edge is, right? Most times you just care about the edge. You actually don't care the internal structure of things. Depend on the pixel values, right? Depend on the pixel values. But how do you tell the difference of pixel value? Right, right. But that's a lot of work, right? Because what that requires me to, let's say, look at this pixel and say, look at all my neighbors. But then I can look at this pixel and look at all my neighbors, right? So for this pixel, all my neighbors are the same. So I say this is not edge. Maybe I say for this is edge. But this is very inefficient. This is very inefficient. I have to go through every pixel and look at all its neighbors and come up with a root for detection. Right? So convolution is basically a way to do that more efficiently. So what you do is this is called a convolutional filter. What you do is for each pixel, you just multiply all its neighbor by -1, multiply yourself by 8, and add it. You do the same operation for each pixel. This can be done extremely efficiently. Okay, this can be done very efficiently. You don't have to write a for loop, for example. Look at all the pixels. You take this, look at this pixel. And what happens? Well, okay, so what happens is, let's say you're here, you're this one here. All your neighbors are the same. You have 8 neighbors, they're all the same value. So you multiply -1 8 times. You multiply your own 8 times, and you sum up to 0. Okay, so this is where this pixel comes from. Okay, this is where this value comes from. So what this filter does is, if let's say you're here, if you have a lot of neighbors that's different from you, you have a large positive value. If you have a lot of neighbors that's same from you, you have either 0 or negative value. So if you apply this filter, you can look at now values as array with high values. You say these are the edges in my array. So this is the idea of convolution. You can extract information by looking at your neighbors, again, taking linear combination of your neighbors. This is a purely linear. Convolution is a purely linear operation. There's nothing nonlinear going on. This is an extremely simple idea. As you look at linear combination of your neighbors, then you can draw a conclusion of things being an edge, for example, things like this. And then that's why you can go from a picture like this to edge detection. So I just care about the edges. You can draw through the edges in the picture. You can have a black and white view of the edges in the picture. This is what convolution does. Right? So you want to extract features, say, this kind of edge features, you apply a convolution layer, right? Apply a convolution sort of filter, you can extract this kind of thing. Okay. This is very good. So this is, right? So, what does, right? So you have all these cameras, you automatically driving cars, looking at the road and people. It's basically running something like this, right? Fancier version of this, but at the fundamental level, something like this. You try to detect where contrast or where the scene contrast. That's why at night it's hard. When it's raining, it's hard. At night, it's hard. You have a very bright background with a bright, object. That's hard because it's hard to determine this kind of edges. Questions again about this? Okay, right. So this again, right? So if you do this kind of convolution filter, you got this picture, then you can decide, a car is here or something is here, right? So you feed it to a neural network and do this kind of determination. Okay, so any questions about this kind of neural network and either convolution or other things? Okay. Yeah, yeah. No. So edge detection is one particular, right? So for each different application, you have a different layer, right? So if each different convolution or filter or layer is doing different, extracting different features, right? So this may be the edge detection layer. There may be another filter that extracts some other features. Yeah. Okay. So again, the underlying math is For O is fairly simple. It just you're taking a bunch of you have an array of numbers, do some linear operation on it, something comes out. Now the magic really is if I 100 layers of this, somehow your computer, some computer is able to train this. That's really hard. Like that's not clear you can do that. Right? But if you taken that you can train it, then the underlying math is not too difficult to see why this works. Sure, yeah, we can do that. Yeah. We can do sort of scene detection, right? You can do edge classification, scene detection. You can do all this kind of thing. And so convolution works well in imaging. In other application, doesn't work so well. For example, low forecasting nowadays is both mostly done by neural networks, and convolution doesn't really do much in low forecasting. Right? There's no reason it should work. Right? So this again, a lot of time, this kind of architecture is part of the hyperparameter is where you try and error. Right? Some human is going to do this. Right? So we haven't really automated this yet. I believe people have tried asking GPT-4 if I want a low forecasting algorithm in this kind of load, give me the best architecture. People have tried that. Didn't really work. Right? So it said something, but the thing is that didn't really work. So it seems that we're not out of the woods yet. You still have some manual tuning here. Right? So the hope is one day all this will be automated. You just say, I want edge detection and feeding a bunch of pictures and something comes out. We're not there yet. You still have some manual work to do for this. Okay. Any other questions? Okay, all right. So we'll stop here today, right? So neural networks. And the next class will do something called unsupervised learning. So for all this, it's basically saying that you have a label of 1 or 0. You're trying to get to that label. Unsupervised learning is a little bit closer to this example is because you have so little non-stable labels. Let's say you run simulation and you want just based on the simulation to determine is it stable or not stable without a label data, right? With nobody giving some label data. So can you do clustering? Can do this kind of detection without labels given to you? And right, so we'll start with that next class. Okay, all right, thanks, guys.